Alright guys, Mr. Armke here with you for NET-125. Let's get into Module 11, IPv4 addressing. So our objective for this chapter is to calculate a subnetting scheme to efficiently segment our network. So we're going to look at address structure, unicast, broadcast, and multicast addresses, private, public, and reserved addresses, network segmentation, and how to calculate IPv4 subnets for a /24 prefix. So let's get into address structure. An IPv4 address is a 32-bit hierarchical address that is made of a network portion and a host portion. We determine this using a subnet mask. To identify our network and host portions, we compare bit by bit from left to right. So the first time we hit a 0, that initiates the beginning of the host portion. So if we see in the graphic to the right, we have all ones to the first 24 bits. So the second we hit that 25th bit in the subnet mask and it's a 0, that means we're going to start counting for the host. Now the process we use for comparison here is called ANDing, not adding, but ANDing. So we're logically comparing two numbers. So if we have a 1 and a 1, it is a 1. If we have a 1 and a 0, because an AND requires both sides to quote unquote be true or on, then we would have a false. So anything involving a 0 in the network portion stays a 0. Anything in the network portion that's true stays true. Now a prefix length or a slash or cider notation is a less cumbersome method to identify the subnet mask address. The prefix length is the number of bits set to 1 in the subnet mask, and because they must be continuous, it's a single row of all of these bits. So we can see here the classful division /8, /16, and /24, and then we see 25, 26, 27, 28, 29, and 30. 30 pretty much is considered the last useful situation because remember we have to take out a pair of addresses, one for the network, one for the broadcast. So here we see the logical operation that I was just talking about for ANDing. When we have a 1 and a 1, that brings us a 1. Anything else brings us a 0. And this preserves only the network portion that lines up with the subnet mask. So within each network are three different types of addresses. Host addresses, which are the bulk of them, network addresses, and broadcast addresses. So usually when we're defining a network, we'll show the subnet mask, the network address, the broadcast address, and the last and first host. Now let's move into some different types of broadcast, unicast, and multicast addresses. Unicast transmission is a one-to-one transmission. We're going from host to host or host to a managed switch, etc. Broadcast is where we go from one host to all other destination IPs. So essentially everything is regenerated except for on the port where it originated. Multicast transmission is a subset of broadcast where specific hosts within that group are sent to, but not others. Now let's look at some types of IPv4 addresses. As defined in RFC 1918, public IPv4 addresses are globally routed between ISPs. Private addresses are common blocks used internally to assign and save the large bulk of IP addresses that are available. So inside the private address range, we can have whatever IPs we like, provided they don't conflict with each other, and then they will be translated to the public IP address externally through our router. Now, because of this, private addresses are not globally routable, at least not in IPv4. So we see that a Class A private range would go from 10,000 to 10,000 max. A Class B is a /12 subnet mask, so that's 172.16.00 to 172.31 double max. 192.168.00/16 is a Class C private address, and that goes from 192.168.00 to 192.168 double max. NAT translates from private IPv4 addresses to public IPv4 addresses. So we have a ton of hosts inside of a network, and the edge router is then able to translate one to the other. There's also a series of ranges for loopback addresses. Pretty much anything that starts with a 127 is considered a loopback, commonly identified as only 127.0.0.1. This is used to test if the TCP/IP stack is operational. The time should always be less than 1 millisecond, and the TTL should always be 128 unless you've set it to a different value manually, because it has not transitioned to any other devices, and it's testing itself, so there's no time of transit, so it should always be less than 1 millisecond. Your link local addresses are going to be the 169 range, 169.254 specifically. That's going to be within the range of what's known as automatic private IP addressing, or APIPA. And when DHCP is unable to configure itself from a DHCP server, the client will then self-configure using one of those addresses. RFC 790 allocated IPv4 addresses into 5 classes: Class A, B, C, D, and E. And we've already talked about A through C. Class D is going to be for multicasting, and Class E is for experimental systems, so everything above 240. Now, classful addressing wastes a lot of IPv4 resources. So classless addressing, where we do borrowed subnetting, ignores the rules of the ABC classes. IANA, the Internet Assigned Numbers Authority, manages and allocates IPv4 and IPv6 blocks to what we call the RIRs, or RIRs, Regional Internet Registries. These are national groups that are responsible for allocating IP addresses to ISPs within that country or group of countries who provide smaller address blocks to smaller IPs and organizations. So you have IANA, then the RIRs, and then you have what are called Tier 1 ISPs, and then Tier 2 down to Tier 3. So you see LACNIC for Latin America, AFRINIC for Africa, APNIC for Asia and the Pacific, RIPNIC, or NCC, for Europe and Russia, parts of Russia anyway. And then you see ARIN, which is the American Registry for Internet Numbers. So that's North America, continental US and Canada. So let's look at some network segmentation. Many protocols use broadcasts or multicasts. So ARP, of course, uses broadcast to find other devices. DHCP uses broadcast. Broadcasts are propagated on all interfaces except for the origin. The only device that stops broadcasts is a router. They do not propagate. Each router interface connects to a broadcast domain. The domain covers all of the hosts and devices within that broadcast area that will accept broadcast packets. The problem with large broadcast domain is that these hosts can generate a lot of broadcasts, and that can bring down the network's ability to use its bandwidth effectively. So here in the graphic on the right, we see one subnet of 400 users being split into 2 subnets of 200 users each. This means that if there is a broadcast on now LAN 1, it will only affect half the users it normally would. Broadcasts by nature are wasteful, but they are necessary. So by segmentation, we can make the necessity of using broadcast flows much more effective. So here we can see a building subdivided into 5 floors, each with their own subnet on the top. In the middle, we can see implementation of different security policies based on departments. And we can also see segmentation based on devices, hosts, servers, and switches. So let's take a look at how we actually subnet an IPv4 network. So most often we use our classful octet boundaries, and that tends to be pretty easy. Using longer prefix lengths borrows network bits from the hosts and decreases the number of hosts per subnet. So for a class A or /8 subnet, you can see that the number of hosts per network is about 16.8 million. It's quite a lot. When we go to a /16, we've reduced the number of octets by 8 and have gone down to about 65,000. We do a further 8 for a class C, and that gives us about 254 hosts per network. Now that's pretty good for most businesses and small buildings. You usually don't need more than that. So here we see, for example, using a class A address with a /16 mask, 256 possible subnets altogether, and then we see that there are 65,000 ranges of hosts per subnet. And we've got our broadcast set up, and then we can see the comparison to a class C subnet mask instead using a /24. So B versus C. Now here we see some borrowing for a 25 through 30. And we can see the number of subnets and hosts kind of invert a little bit. So 2 times 126, which is, well, of course I'm not going to expect to hear things back, but 252. And then we have 4 times 62, which is 248, 8 times 30, which is 240. So we see that while the numbers are close, they are diminishing each time, and that's because we keep adding the broadcast address and network address for each subnet. So let's go ahead and look at subnetting a /16 or a /8. So here we can see the network and host bits being changed over and bolded out to reflect the number of subnets and hosts per individual unit. So we see 16,384, so that's what, 32,768, and then 6 times 8, so that's 480. Yeah, it's about the same transition. It's just a little bit more sharp because we have more host bits to work with. Now, let's consider that we have an enterprise that requires at least 100 subnets. It's pretty aggressive, right? So we would need to look at the nearest power of 2 that could encompass 100 subnets, 128 in particular. So that means we would need to borrow 2 to the 7th is 128, so 7 bits would need to be borrowed to create 128 subnets. Now, that's out of the 14 bits that we've got in the internal structure. So we're cutting across a fair amount through the 3rd octet and into the 4th. So what about a small ISP that needs 1,000 subnets? So we have to borrow up to 10 bits. So 1024 would be what we support for that. So we would need to satisfy that requirement. So based on using a /8, where we would have a number of bits to be borrowed, we have an 8-bit subnet mask out of a 32-bit address. We still have 24 bits. We can't borrow the last 2, so that leaves us with 22. There's a lot of coverage we can do with that versus a /16. What I tend to do more often than not when I'm setting up a network is subnetting to meet specific requirements for hosts, not necessarily subnets. So in this case, we have an example of a corporate network, an enterprise network. So we have an intranet, which is an internal network with private addresses. We have a DMZ, which is company allows their servers to be internet faced. The DMZ is essentially a space between 2 firewalls to help keep them secure. And in this case, for each of those, we could possibly use a /8 network with a /16 or /24 network boundary in order to set up these subnets. The DMZ devices, of course, have to be configured publicly, but the intranet stuff can be set up privately. So here we can see the subnets being tracked for the maximization of our subnets and minimizing of wasted host addresses. So we have to consider the number of individual subnets we need and the number of hosts that are required for each network to be successful. So let's say we've got to handle 100 hosts. Well, we got to look at a /25 because we need at least 100, and the closest to that is going to be 126. 62 is way too low. If we needed 20, then we would be looking at a /27 because 30, while high, is still not too wasteful, and it covers more than the /28, which would only be 14. So we have an example here. A corporate headquarters has been allocated a public network address of 172.16.00/22. So that means that we have 10 host bits total that we can work with. That gives us just over 1,000 host addresses. Now there are 5 sites and 5 internet connections, so we need 10 subnets with the largest requiring 40 addresses. So we take 10 subnets with a /26 mask. There's also what's called VLSM, and this is where we, instead of breaking these hosts apart into equal segments, will subdivide and subdivide and subdivide to optimize usage of our hosts. So given the topology here, building A, B, C, and D with 4 routers, 3 links between 1 to 2, 2 to 3, and 3 to 4, the largest number of hosts is in building D, so that's 28 hosts. A /27 would give us 30 hosts in range, 32 addresses total, and therefore it would support that topology. But could we not do better with building C? Building C has 15 hosts, so 2 to the power of 4 is 16, but no, we could then have an issue with our network and broadcast addresses, so we got to stick to the 27 so far. Now, we also have WAN addresses that only need 2 each. So we can go ahead and say, all right, well, let's go ahead and break up and do 3 subnet addresses that are able to run /30 that only have 2 hosts apiece. So here we can see how the original subnet was set up. We can see that we've got 8 segments of 30 each, but we take one of those 30 host segments and break them into 8 hosts of 2 hosts each. So 32 becomes 8/4. So 4 is our 2 hosts, broadcast, and network ID each. So we're able to then assign that to our WAN links and reduce the amount of wastage that would be involved. So here we can see in this case we've got 28, 15, 20, and 25. That all fits pretty close within the /27. Now we're going to use the /30s for our router to router links, and we have optimized our network segmentation for this particular assignment. Now let's take a look at structured design. It's really crucial to develop a scalable solution to an enterprise network. To set up an IPv4 network addressing scheme, we need to know how many subnets are needed, how many hosts a subnet requires, what devices are a part of the net, which parts of your network use private addresses, which ones use public. There's a long list. We can also examine the needs of a network's usage and how subnets will be structured. So performing a network requirement study will allow us to determine how each area will be segmented. So let's take a look at how many subnets we need, how many hosts per subnet, and then we can determine our address pools and VLAN pools. Within a network, there are different types of devices that require addresses. End users, of course, these are going to use DHCP to reduce errors and burden on support staff and provide automatic addressing. IPv6 can also use DHCPv6 or SLAAC. Servers and peripherals, of course, these should have predictable static IPs. Servers accessible from the internet have to have a public IPv4 address and will be often accessed using NAT. Intermediary devices are assigned addresses for network management, monitoring, and security. And then the gateway would be your router and firewall devices for hosts within a network. When you're developing your scheme, it's generally recommended that you have a set pattern of how addresses are allocated. So generally what I recommend is to sit down, write out all of your hosts, all of your different segmentation pieces, and then just kind of spitball for a bit and see how it all fits together. You want to do that all on paper because when you start trying to assign them to devices, then it's really hard to go back and correct without creating a lot of confusion. So here are our new terms and commands for the chapter. You can see that we've got things like broadcast address, network address, unicast, broadcast, and multicast transmission, NAT, loopback, APIPA, public and private addressing, classful and classless addressing, VLSM, octet boundaries. These are all things to familiarize yourself with, but more importantly, it's better for you to go in and practice. So if you haven't gotten a chance to do so, there are VLSM practice items on NetAcat as well as on our NetLabs site through Stanley. So I suggest that you take advantage of that as much as possible because you will most definitely see this again. Thank you again, as always, for your time and attention. It's been my pleasure to guide you through this lovely world of subnetting. If you have any questions or concerns, you can always contact me at jearmke063@cfcc.edu or my Google Voice number 239-7814. Hopefully, you'll have a wonderful rest of your day, and I will catch you next class.